Hi everyone, Mr. Boltri here bringing you video 2.5 where we're going to talk about normal force, specifically as they apply to ramps. To do this video, we're going to define normal force, talk about the differences between normal force and weight, which remember is a synonym for the force of gravity. And then we're going to talk about how normal force applies to ramps and how that sometimes causes us to need to shift our coordinate system. So to get us started, what is normal force? And to talk about that, let's take a little detour and talk about the force diagram for this bowling ball. So I'm holding the bowling ball and it's stationary. Because it's stationary, we know by Newton's first law that the forces are balanced, constant velocity balanced forces. So the forces acting on it are gravity and the force applied by me on the ball, force gravity by the earth on the ball. We know they're balanced because it has a constant velocity. And it's just kind of hopefully self-evident to you that I am exerting an upward force on this ball. If I were to ask you to hold a bowling ball, you could probably do it easily for a couple minutes, but after a while you would get tired because of that force that you are exerting. So let's think about this as we look at the next example, which is this apple on the piece of balsa wood. So the question is, what is the forces acting on the apple? And again, the apple is stationary, so we know the forces have to be balanced. There's a gravitational force down and some force acting upward. We'll just say that it's the applied force by the balsa wood onto the apple. And we can tell that there's an applied force because of the way that the balsa wood is deforming or bending. It actually looks like it might be exerting an upward force. So let's keep that in mind as we look at the next example, which is a bowling ball sitting on a piece of foam. Again, stationary, balanced forces, constant velocity. So there's the force gravity downward, and there has to be some applied force upward. So even though it seems like it might not be, the foam is applying an upward force to counteract or balance out the force gravity, which is, we know because the forces are balanced, balanced force is constant velocity. But we can just look at it and tell that the foam is exerting an upward force because of the way that it deforms. So it kind of makes sense for us that the foam is exerting an upward force. And finally, let's keep all of these examples in mind as we look at the fourth and last example, which is a bowling ball sitting on a flat table. So again, according to Newton's first law, balanced forces, because it's stationary, constant velocity. And so we look and we say, well, if there's a force gravity downward, there has to be an applied force pushing upward. But what is applying that force? Because it seems like the table is just kind of in the way. The table can't be applying a force because it's an inanimate object, and inanimate objects can apply forces. But if we look back at the previous examples, like let's say the foam is an inanimate object and it can apply a force because of that deformation. We can see the force with our eyes. But the issue with this bowling ball is that it's harder to see the force with our eyes because it looks like the table doesn't even care that the bowling ball is on top of it. But if we were able to zoom in on a microscopic level, we would see that there actually is just a tiny, the smallest, talking on the scale of nanometers, amount of deformation in the table. So even though it's way smaller, the table is still doing something to exert that force. So the table, even though it is inanimate, is still in the same way that the foam is deforming, or not in the same way, but in a similar way on the scale of nanometers, the table is also deforming just a little bit, which kind of makes sense because if I were to drop the bowling ball into the table, you might see a little dent because it would have to exert quite a bit more force to balance out the force of gravity of the bowling ball. So all of these forces that we've been talking about, I've been calling them applied force by the table on the ball, but it has a specific name. It's called the normal force. And so normal force is what we're going to be talking about in this video, and all of the examples that we have just shown have been examples of a normal force. Because what is a normal force? It's defined, and probably worth writing down, as the force that is exerted by a solid surface to stop an object from passing through. So in this example, the solid surface was the table, and the object that would have passed through it otherwise is the bowling ball. So it's not that just that the table is getting in the way, it is actually actively exerting, let me highlight this word, exerting a force in the upward direction. So the table is doing that. And so normal, we think about normal as just like sort of the standard or the thing that everybody's doing it. It's totally normal. But the word normal in the physics context actually comes from a different meaning. It actually comes from the Latin root word normalis, which means made with a carpenter's square. And this is a carpenter's square. And we'll talk about why the normal force came to mean made with a carpenter's square or normalis in a minute when we talk about ramps. But before we talk about ramps, I did want to clear up something that seems to have been a source of confusion as we've been talking about normal force and weight so far. So remember, weight, up until this point, all of these examples, you'll notice that the normal force was a balanced force with the force of gravity, which is a synonym for weight. So remember, force of gravity and weight are synonyms. And we'll notice that in all the examples I showed you, the force normal did equal the weight. And that is often true. In many cases, that's true. But I want to show you that it's not true in all cases. So let's look at the example of me correctly using a scale. So as I stand on the scale, let's say I'm stationary, so the forces on me are balanced. There's a downward force of gravity or weight acting by the earth on me, and then an upward force by the scale onto me. So these two forces are balanced, and the reading on the scale, which is the normal force, equals my weight, which makes sense because we stand on scales typically to try to figure out our weight. And we do that by looking at the normal force, assuming that I'm using the scale correctly. But if I use the scale incorrectly, let's say as I'm standing on the scale, pulling up on a string, as I pull down on the string, the string pulls back up on me according to Newton's third law. Force by Boltri on string equals the force by string on Boltri, just equal magnitude, opposite directions. So you'll notice that there is a force tension pulling me upward. So because I'm still stationary, my forces still have to be balanced. So there's a weight that's still pulling me down that hasn't changed at all. The force gravity didn't decide to pull on me less. The force gravity is always pulling on me the same amount, assuming that my mass stays the same, which between 1201 and 1202, my mass isn't going to change at all, even though if I might be gaining weight or losing weight, which really means gaining mass or losing mass, in a minute, my mass isn't going to change, so my weight isn't going to change. But because I pull up on the force, because I pull down on the string, so then the string pulls back up on me, then my force normal has to decrease in order to cause the forces to be balanced. Which you can actually see on the scale, it goes from 170 pounds to 160 pounds, which does not mean that I lost weight. It just means that the force normal is the reading on the scale, which is the force normal, is no longer telling me the weight. So scales read force normal, and scales often tell us the same thing as the weight, but not always. That's really important to understand. The other common example of when the normal force does not equal the weight, so there's two. The first one is when there's multiple forces in the vertical direction, either acting upward or acting downward. The second one, which we've seen several times already, is the classic elevator problem. So if you are accelerating, then the forces have to be unbalanced. So either the forces in the upward direction have to be greater or the downward direction have to be greater. And because weight doesn't change unless your mass changes, which it's not if you're just standing in an elevator, then that means the normal force has to change. The floor is going to push on you either extra hard if it needs you to accelerate upwards, or the floor is going to not push on you as hard if it's trying to cause you to accelerate downward. So that is kind of the summary on why normal force does not always equal weight, but it often does in certain circumstances. But now let's talk about another circumstance where force normal does not equal weight, and that's ramps. So if AP isn't feeling in a nice mood, they might give you a problem with a box that's just sort of on a level ground. So then if it's stationary, you know the force normal is pointing up and the force gravity is pointing down, and it's a really easy, great, awesome problem. But things aren't always that easy, especially as far as AP is concerned. And in real life, it's not always that easy. For example, the baggage handlers at airports use something where the normal force is not going to be pointing straight up in the vertical direction. Another way to say that is sometimes it's nice to be the baby sitting on the level ground, but when we grow up a little bit and want to try harder problems, we can try to be like the toddler and sit on a ramp and see how things change and are different. So let's look at the problem of just a box sitting on a ramp. We can say that this is the baggage handler at the airport, and talk about, well, how are things different? And in order to answer that question, we have to go back to our handy dandy carpenter's square, normalis made with a carpenter's square. So why is a carpenter's square relevant to normal force? Because if we line the carpenter's square up with the surface, we can see the direction that normal force points, because normal force always points perpendicular to the surface. That is just how normal force works. It's how it's defined. It is why it is named what it is, because it always makes a right angle, exactly like the carpenter's square, because it's perpendicular to the surface. The surface is the thing that's pushing on the box, so the surface pushes in the direction that the surface is perpendicular to the surface. So again, something that's just worth writing down and knowing about how normal force works. So now that we have the normal force here, as we talked about in the equilibrium and dynamics video, we're going to have to start looking at the other forces acting in the situation and try to do some calculations with those forces. So obviously, if it's on any planet, if it's near any massive body, there's going to be a force gravity pointing towards the center of the planet, which for most situations is straight down. Actually, maybe all situations, at least if you're on the surface of the planet, I'd have to think about that one. And then I'm going to go ahead and do a preview for my next video, which is about friction, and say that the direction of friction, because the friction is caused by the rubbing together of the two surfaces, the direction of friction is always parallel to the surface. So you'll see the force normal is perpendicular and the force friction is parallel. So if we were to try to solve this problem using the equilibrium or dynamics, we would have to break the force normal and the force friction into their x and y components. So this force normal is a little bit to the left and up. This force friction is a little bit to the right and up. So we would need a horizontal and vertical component for each of those two forces, which then instead of having 1, 2, 3 forces, we have 1, 2, 3, 4, 5 if we're looking at all the components. So that's totally fine, and we can solve it that way and it can work. But we are also in control when we are doing physics problems. So one thing that we might choose to control is, well, instead of using the XY coordinate system, why don't we just turn the page a little bit and then look at it like this, which is totally acceptable. We get to choose as physicists what coordinate system we want to use. So in this situation, why don't we just choose X to be over this way and Y to be over this way, which is totally acceptable. You can call this direction X and this direction Y. And you might ask, well, why would we want to do that? Well, then you'll notice that the force normal is completely in this direction, and the force friction is completely in this direction. So then the only force that we would need to break into the two component vectors would be the force gravity, which has a little bit in this direction and a little bit in this direction. But for me, I do not like turning the page and then calling this sort of angled view X and Y. What I would prefer to call it is something that's more descriptive, because I think of X as being horizontal and Y as being vertical. It's okay if you call it that, as you've seen in AP problems before, but it's my preference, just so that I get less confused, and I recommend that you do the same, is let's make up a new way to call these things. So since this direction is perpendicular to the surface, sometimes physicists use this symbol to mean perpendicular, and geometrists use that symbol too. And since this direction is parallel to the surface, we can use two parallel lines to just show that we're talking about the forces that are perpendicular to the surface and the forces that are parallel to the surface. And if the object is in translational equilibrium, or AKA it's moving with a constant velocity, we know that the forces in the x direction and the y direction have to be balanced. In the same way, the forces in the perpendicular and parallel direction also have to be balanced. So if we were to choose this coordinate system, what that would look like is, so this is already entirely in the perpendicular direction. This is entirely in the parallel direction. And we just need to find the parallel and perpendicular components of the force gravity, which is kind of like this direction and kind of like this direction. And so we can use trig to do that. And then we get the force gravity, the parallel component, and the force gravity, the perpendicular component. And then we can see if the forces are balanced or unbalanced, and then solve for certain quantities, including acceleration, from there. So that is kind of an overview of force normal, specifically as they apply to ramps, and how sometimes it's useful to shift our perspective, and instead of looking at the XY direction, maybe we look at the parallel and perpendicular direction instead, just to sort of simplify problems, because here we have two forces and one that we had to break up into component forces, as opposed to having to break up two into component forces, which just is a little bit more complicated. So We will start solving problems to do with ramps and normal force in our next class, which I am looking forward to doing with you. But for now, this is Mr. Boltri wrapping up video 2.5 on normal force and ramps, and go Bears.